We will have an overview talk or a survey talk at the beginning, and that's Andreas Nautsch from the now from the EURECOM Institute in Sophia, Antipolis, and formerly with the Technische Universität Darmstadt. He will speak about preserving privacy in speaker and speech characterization, and you know that privacy is an important topic. We now have a special interest group in ISCA related to it, and we're looking forward to your talk, Andreas.
Thank you. So I present the survey, which is recently published, online available. Basically, I was leading a collaboration of more than 20 authors coming from different fields, including study of the law, biometrics, cryptography, speaker recognition, so if we do biometrics with the voice, and speech communication, which in this talk we will consider as the wider, larger speech applications. So speech applications are everywhere in digital assistants and voice-driven interaction technology. Again, the main part of this talk will be focused on the biometric identity, speaker characterization, as most of our authors are from the background, but we're also looking into non-biometric tasks about the characterization of speech and how we can preserve privacy in there. So privacy preservation is a legal obligation nowadays, which frameworks in the US and the European Union, and there are cryptographic solutions, which I will outline as well. So in the beginning of the talk, I will talk about privacy in the US and European legislation, then talk about biometric information protection, what the biometric community has developed, then about cryptographic solutions for speech technology, and conclude the talk. So about privacy in US and European legislation. First of all, a disclaimer. We don't have any legal authoritative competence, which means who's the legal authority? That's a judge. We are not judges. What we will present here is our opinions, and please see them as such. So first of all, my legal colleagues reminded me there's not a single or universal definition in legislation of the term privacy. That's the first remark to take. So what are privacy and data protection? Privacy is originally defined by Warren and Brandeis in the US about 150 years ago as the right to be left alone. In the US, there are 4 types of privacy. There's informational privacy that is referred to as data privacy as in this talk. Then there's physical privacy, decisional privacy, and proprietary privacy. In the European level, on the other hand, privacy is regarded as a broad term, not susceptible to any exhaustive definition. And it's stated in the Article 8 of the European Convention on Human Rights and on the Article 7 in the Catalogue of Fundamental Rights and Freedoms. So it's inherently rooted within European legislation. Data protection, on the other hand, means simply using safeguards so that we can protect sensitive information. So at the European level, recently the General Data Protection Regulation, the GDPR, Regulation 2016-679, was enforced, and alongside with it, its sibling directive, the Police Directive, Directive 2016-680. They were both put in place on the same day. Both of them define biometric data as personal data resulting from specific technical processing relating to the physical, physiological, or behavioral characteristics of a natural person, which allow or confirm the unique identification of that natural person, such as facial images or dactyl corpus data. So the question that here comes is, what is unique identification? And there are different opinions. So one could argue it's just to use a reference of the biometric identification modality. So we have only one-to-n comparisons. We have one reference and we compare it, or we have one probe and compare it against lots of references. But it could also mean to find a threshold of identification from a data protection perspective. So it would consider verification and identification in biometric terms. This means one-to-one, but also one-to-n comparisons. And the main difference is that, for example, that we can authenticate ourselves to a service but if we think about, for example, law enforcement, we are interested there into singling out a biometric identity of a short list of suspects, for example. And the GDPR doesn't directly talk about speech data, but we can relate to other biometric modalities, for example, faces. So recital 51 of the GDPR on photos of faces, they should not systematically be considered as biometric data if not processed through specific technical biometric processes. So if you just have a picture and we want to show it, that's a different use than a biometric recognition. So biometric data on its own is not the sole sensitive data. There's also racial, ethnic origin. There are political opinions, religious beliefs, philosophic beliefs, and health data, among many other sensitive data. The GDPR requires a data protection impact assessment. What that is not specifically defined. It's more a requirement for processing if we process on a large scale. So it's an obligation for data controllers and for data processors to look into the technical and organizational measures that ensure confidentiality, integrity, availability, resilience of the data for the processing, and to evaluate the effectiveness of such security measures. In general, we can think about it as the text of the law, what we need to follow, what we can follow. As technical experts, we really like definitions, so we can work on them. But in here, it's also about the spirit of the law, and this one goes more into the direction of that case studies need to be there, and that people need to work on it. And the reason why this is also important is that there are interrelations with other regulations and directives on the European level, if you think about the European Union as a market, for example. So there's the concurrent e-privacy regulation, which is under development, and it will reflect upon the GDPR. But also there's the Payment Service Directive, PSD2, which is basically for online banking regulations, and they also referring to data protection regulations. So about the US level, there are specific acts and provisions in 3 states, namely Illinois, Texas, and Washington. Illinois and Texas have a restrictive definition of what biometric identifiers are. They explicitly say that specific modalities and identifiers that they are that, and everything else maybe is not a biometric. In Washington, the definition is by examples. So they are suggesting, for example, voice prints, and this gives more freedom to the interpretation of what biometric could mean. Then there's the California Consumer Privacy Act. And their identifiers can be extracted from biometric information, which is even more general. At the European level, on the other hand, there's the concept of privacy by design and privacy by default. This means, as with the DPIA, to take technical and organizational measures beyond only security measures. So really, how can we, on an organizational level, assure privacy? And the factors of that is the state of the art, the cost of implementation, the nature, the scope, the context, and the purpose of the processing. So if we change the purpose of the processing, maybe that is an infringement of the privacy rights, and also on the risk to the individual rights on that level. So what is at risk? Then the GDPR states that the data minimization principle. So there's a limitation of data collection to what is strictly necessary. In speech communication, we love to annotate data sets. So is there a conflict or not? How to deal with that? If you find the phrase privacy by design, this is more like a policy principle. If you find by design and by default, this is a legal obligation. Okay, so biometric information protection. In here, I will talk about standardization, so what the biometric community has already enforced. So what is biometrics? From my personal perspective, it's secure authentication and applications for end-user convenience. An end user could be someone who uses a smart home assistant. It could also be border control, where they're just sparing to employ officers. It's for end-user convenience. In standardization, on the harmonized biometric vocabulary, biometric is defined as the automated recognition of individuals based on their behavioral and biological characteristics. If we compare it to the other authentication factors that are well known, like passwords and PINs that are knowledge-based, or passports and smartphones, which are tokens, a fingerprint or our voice With knowledge and token-based, we can lose them. We can forget them. We can just pass them around. But also we can forward them. We can just go to our colleague and say, go to the printer room, take my key. Or we can lose them, they're going to be stolen. So with biometrics, that's usually not the case. But we cannot renew our biometrics. With a password, we can just enter a new one, and then you have it renewed. With biometrics, we cannot do that. When it is stored in the database, it is stored. So how to protect biometric information and more or less for the purpose to have renewability. So the ISO IEC standard 24745 is a standard on biometric information protection, and they have 3 requirements. Unlinkability, so this means if there are, for example, 2 data sets, one at a healthcare and insurance and one at a bank. You don't want that someone gets both data sets and then can say, okay, that identity, rich and sick. That's a thing you don't want to. Renewability means if I have protected biometric data stored in a data set and I want to change the protection scheme from one to another one, I don't need to recollect speech data from the data subject. So is there a way of changing this? And irreversibility means when data is protected, I cannot go back to speech data, not in feasible time. So the standard suggests a general system design. In biometrics, like with passwords, we first need to put the initial reference. This is called an enrollment process, and afterwards we can do a verification. So this chart right now is just on the enrollment phase. So we can present our iris, our fingerprint, or our speech to a sensor. And then in the enrollment, in the signal processing, there's a feature extractor and a pseudonymous identity encoder. This encoder has 2 outputs. On the one side, it's the pseudonymous identifier for the reference stored in a data set, but there might also be auxiliary data. And in biometrics, they usually consider operations like XOR, and they have random bit sequences, which are these auxiliary data. Or they work on integers, but for us, as a speech communication community, we are more interested in float values, just as a foreshadowing. During the verification, again, we present our biometric characteristics to a sensor and have a feature extraction there. And then we have a pseudonymous identifier recorder. It uses, because of the identity claim, we know which auxiliary data to load. And with the help of that, we can record the pseudonymous identifier of the probe. And then we can have a protected comparison from which we get a score we can compare to a threshold, and then we make our conventional decision. Okay, so far so good, but how to measure this? So there are different figures of merit. In a related work of a colleague, they are proposing an unlinkability metric. In there, they are discussing mated and non-mated instances. So if we have 2 data sets and the data is of the same person or not of the same person, if the score distributions of some linking function are completely separated, we have a fully linkable scenario, because we can say the green curve, where we have the mated instances, we can clearly classify them from the non-mated instances. So, and only when the linkage functions have these overlapping, we talk about semi-linkable, and when they're identical, we cannot make any decision, any linkage, and then we have unlinkability. But there are other measures as well. So this is considering the biometric scenario, but what about the non-biometric scenario? So in our survey, we outline, inspired by differential privacy, that there could be a degree of privacy in non-biometrics. So if we think about an algorithm A, which we put in data, we get a likelihood for the data. That's one thing. But if we then put additional data, which comes from one individual, so biometric data, it shouldn't change the outcome of that algorithm, because it's a non-biometric algorithm. So what's the maximum magnitude in that difference? The other way is more motivated from how do we do score computations in speaker recognition, in voice biometrics. So there we can more talk about the degree of biometric evidence that's still persistent within a non-biometric application. So we can compare the likelihood of evidence, so a speech sample, given the proposition it's the same subject against it's a different subject. We can just compute, so to say, oracle log likelihood ratios. And ideally, they should be 0 if it's non-biometric data. But as soon as there's biometric inference possible, the maximum will tell us of the absolute, what's the extent of the degree of biometric evidence that's still persistent. Okay, this was more the empirical solution to it. The cryptographic solutions are different in nature, and here I will show what technology is out there for biometrics and for non-biometrics. So, cryptographic solutions, we need to formulate some kind of question, and this goes in the direction of how to prepare functions and data such that the correct outcome can be derived from a computation which operates on that protected data. So usually there are two ways, and one can be broadly described as encryption and the other one on secure computation. In encryption, we send encrypted data to a function which has a database in the background where our encrypted reference, for example, is. And then this encrypted function can compute the encrypted comparison value. So, for example, our biometric comparison score. And then the end user can just decrypt it and has it. On the other hand, there's secure computation, which requires interaction. So to say, a server is introduced as a second party, and here the figure in blue. And there the idea is, can both parties send data chunks, which can be in plain text, but can be obfuscated or randomized to some extent. And then these functions can securely compute the outcome. The common example for this is the millionaire's problem. So you have two very rich persons, but neither of them want to say how rich they are, but they want to know who is richer. And there are communication protocols within secure communication that allow you for them to send pieces and chunks of data back and forth. And in the end, you have the outcome of the decision, for example, who is richer, or for us, who's in behind the biometric identity. Okay, so the question is now, how does this work? In cryptographics, usually there are assumptions. One of them is computational indistinguishability, which means when I run the same protection scheme on plain text data, I have two different outcomes of the same protection scheme just applied twice. And I cannot say if they come from the same plain text or from another plain text. That's very loosely the definition, but more or less the concept. And the other one is cryptographic hardness. So for example, it is easy, we can easily compute the product of two numbers, but it's hard to factorize numbers into their primes, especially when they are large. So it would take forever to do this. And this already pinpoints how cryptography and secure computation work. There are formal definitions about the infrastructure, how our services operate, the communication between servers, end users, entities involved, and who carries out which computation part. And this allows for formal proofs such that we can actually prove that there is zero knowledge for the parties involved. And again, the well-established methods for that are secret sharing based or public key cryptography. In the following, I will give 4 examples that are the technology is already proposed for homomorphic encryption, secure two-party computation, differential privacy, and hardware-assisted security. So, for homomorphic encryption, the most known one is Payet homomorphic encryption. We proposed it for speaker characterization last year. And then there, the idea is to preserve algebraic structures. So we are in the lower scenario where a data subject sends encrypted data to a function, to a server maybe, and there's encrypted data in the background, and it computes the comparison score in the protected domain and sends the score back maybe to an authentication server. So the idea is if you, for example, say group G is our plain text data, that's the operations that we are used to. If we want to compare G and G prime, so reference and probe data from biometrics, we get a comparison score. That's the operation between the two. Now the question is, can we have an algebraic structure H, where we just map all the elements of our group G, where we can do the same thing, and we have H and H prime as representations for G and G prime, which have the same homomorphic meaning. And if we have them in the encrypted domain there, we would compute the encrypted score. Going back, so finding the inverse of this mapping function f just means to decrypt the protected score. Now, most of the cryptographic solutions that are out there operating on binary or integer data. But we have floats, so that's the example on the right-hand side. And what we are interested in usually in speaker recognition is called probabilistic linear discriminant analysis, PLDA. And we are thinking there about a subspace, where in here speakers are encoded by different colors. They align in a linear subspace, and then we have within and between variances. And with that, we can do a probabilistic inference if it's the same speaker or not. But in there, we don't have integers, we have floats as data. So the challenge is that the computations there rely only on integers. And to do these encryption functions such that there's enough cryptographic hardness, so to say, we need to have large keys, large private keys and public keys. And these already foreshadows that there is a computational cost, which is huge. And it's a trade-off that we then need to pursue. Going to the next one, secure two-party computation. So that's the second example. It's also proposed for speaker characterization as a work from colleagues of mine in Darmstadt who are working on cryptography. And the idea there is that only random data is shared. And that we introduce to the data subject, we introduce two servers, not one server. And this change of the architecture allows us that we send to one server, we send random data. To the other server, we send our original biometric data, but so to say, minus the random data. So what both see is random values. So then these servers can communicate with another to securely compute partial outcomes. In there, we need to have a cryptographic assumptions, meaning they are not colluding, because if they would just fuse the data they have, they would know. But this is, again, the meaning of we need to have some assumptions which need to be reflective of the organizational measures that we take. And after the computation of the secure partial outcomes, we can reconstruct the final function outcome. The downside here is the computations might be fast, but the communication cost might be high, because then the servers need to talk, and they don't only need to talk once or twice, as it's indicated in the figure, there are more communications necessary. And if the channel is heavily overloaded by other communication traffic going on there, then the outcome is revealed later. So another solution that's currently widely debated in machine learning, for example, is differential privacy. This was proposed for non-biometrics, for the speech characterization task, but it's easily transferable also to speaker recognition. This deliberately encourages the data leak for the sake of usability. So in there, they're usually talking about some epsilon differential privacy, as we saw in the metric before. Again, we have our algorithm, which we give adjacent data sets, and we expect the same outcome to happen. Now, what is the absolute magnitude if we add biometric data, for example, in changing the outcome of these functions? So let's say some probabilistic measure. And if that's below a specific epsilon value, we can say it's epsilon differential privacy. These usually allow for faster computations, but there's information leakage. And these solutions were, in our community, already proposed in 2010, 2012. And the usual ideas there is if we want to have a multi-party collection of data, so if we have many data sets at different data hosts or data controllers, how can each of them contribute the data but without really revealing it? So how can we do a multi-party collection on private data? Regarding deep learning, where we usually have an objective function, there was an idea of perturbing, adding some noise to these objective functions such that privacy preservation could be granted. Then another perspective on this was the objective function is usually optimized by some gradient descent method in machine learning. So how to reformulate this stochastic gradient descent so that we can protect on privacy. Then in last year interspeech, out of the cryptographic community, hardware-assisted security was proposed, relying on the Intel SGX technology for speech recognition. In there, the idea is that a server which has a computational unit, we have an enclave, an SGX enclave, that's the middle in the figure, and there we can process securely plain text data, but only in very small, let's say RAM size, so very small data amounts. This enclave has a private key and can generate public keys. So with the public keys, users and vendors can send their data encrypted to the enclave, and the enclave can encrypt it. But the thing is, the enclave can only encrypt it bit by bit. So to set up the entire process between a user, a service provider, and a vendor, so we need to have an initialization phase and a preparation phase of the initialization to happen. In the initialization phase, for example, we can put acoustic models and linguistic models that are here indicated by the databases with AM and LM that are filled values, so to say, but we need to prepare the entire system that the system is aware of that these values are coming. And then in the operational phase, because we only can there deal with small data chunks, we need to have several rounds of communication for our speech recognition engine until we have the final output that goes back to the user. Okay, so to conclude the talk, I will make now several recaps. So we talked a bit about legislation. The main reminder here is, or the major takeaway, there's not a single or universal legal definition of the term privacy. What we maybe can do is we can have a qualifier and then privacy. We can talk about biometric privacy, for example, and then things become clearer. But talking about privacy in general is a hard topic. In the European legislation, there's privacy by design, privacy by default. So we need to have measures not only on the security level, but also on the organizational level. And then as an outcome of this discussions with my legal colleagues, the legal community, the legal studies, they understand biometric face data and fingerprint data pretty well because they're around for many years, for many decades. But the harmonization of to get understanding of speech data better is like on the same scale as harmonizing the different methodologies between speech communication and the legal community, which then also reflects upon the vocabulary that they use and that we use. And if we want to progress further with them together, we also need to talk about the cycles within their research and our research lives in. For the biometric information protection, the good news is there's already a standard which can be used. For non-voice modalities, usually they're thinking about integer data types and the biometric data that they concern of high precision when they're captured. Whereas in speech data, we are aware of ambient noise, so we have more uncertainty that we need to talk about. And usually the numerical operations there are simple, like an XOR. For the cryptography, solutions are specific to assumptions, and they need to be reflected in how we design and operate our systems, our technology. The widely used methods operate on integer data types or binary data, but not on floats. And there's a complexity trade-off for the computation amounts and communications amount that there are. And usually cryptography, in its name, it's from graphene to write, it's security for messages. So a question that we might ask to the cryptographic community, is speech data a message or a medium representation? So, because if we think about speech data, in communication, speech is a medium to exchange or impart information. It is not a message as such. So, our speech captures have variable precision, and we need to have some principled uncertainty propagation when we do recognition. And as already shown for speaker recognition in the example, we have a probabilistic inference of the decision outcomes using evidence, such as speech samples. And there we usually have float data types. And what we are used to do is when we train or operate our speech applications or do research, we compute determinants, we do matrix inversions, we have matrix multiplication, we have Fourier analysis, we might have sorting. For us, this operates fast because we don't need to concern cryptographic solutions, but these are expensive in the cryptographic world. So what's next? We proposed a special interest group within ISCA on security and privacy in speech communication, SPSC. Security to be free from threat or danger. Some of you might be already familiar with the ASV spoof challenges. And then privacy, to be free from public attention. And for that, we have a special session on Thursday. And that's the starting point. So what is more of interest for us is also what is the perspectives of legal and cryptographic researchers. How can we combine these communities? And for speech communication, we need to understand the impact to our technology and to the way we do research. And this is an interdisciplinary effort. So we need to talk about usability, speech, the law, forensic science, cryptography, cognitive sciences, and so on. And what we will do is to coordinate workshops, seminars, organize satellites, research challenges. For next interspeech, there are 2 challenges in planning. We hope to keep you posted. And the support that we have are not only from the speech technology, where we have many researchers supporting us, but also from cryptography and from legal studies. Thank you. Other questions?
Thank you very much, Andreas. Okay, any questions? While you're thinking about it, maybe I can ask you one. You focused quite a bit on what I consider to be the kind of processing of speech. I guess most of the cryptography is associated with the processing. Do you think storage of speech, either in the short or long term, is adequately covered by existing GDPR legislation?
I think we might need better informed legislation. I continued work with the legal experts and will present it on Thursday. If we store data, we are just used to use it for another experiment. If we do ASR or we do speech recognition, maybe we want to then look into, can we also do biometrics with it, or can we do emotion recognition with it? We have good quality in the annotation of data sets. But for the legal perspective, this is more like a function creep, because you're changing the purpose. And for that, also the storage is important, because we need to think about if we are storing it on a single device, if it's locked away without internet access, if it's in the cloud. Maybe there are third parties involved in the storage. What can they see? Can they be trusted? Maybe they are semi-honest. Maybe they want to snoop into the data and learn just something out of curiosity. To what extent do we want to limit this?
Thank you, yes.
Thanks for the interesting and insightful talk. Coming back to your last question, is speech the medium or the message? As we have seen here in interspeech conferences, so many paralinguistic and whatever challenges trying to find out what you can read from the voice signal, from depression to drug abuse to sleepiness to whatever. So I would, and we are still not at the boundary of finding out what can be read with which precision from the speech. So is that somehow reflected in these legal frameworks you have presented?
I don't think so. Again, this is case studies. So we see our entire community as one. But if you want to assess it from a legal perspective, you need to go case by case and look into the details and look also what is the operation where it is in, if you do emotion recognition or if you do depression analysis in healthcare.
We don't know what someone will do with that signal, so we just have the signal. You say it's a medium, but I say there are thousands of different messages in there.
I was actually discussing this with a cryptographic colleague the other day. And to them, they go from the information theory perspective. If you have audio data of some length, some duration, you have different bits, and the amount of bits that you can permutate, that's all the information that is in there, right? So there cannot be more information. Now, it's just information depends on the question you ask. You can ask for emotions, you can ask for depression, for the content. So that's why we need this special interest group to achieve understanding not only for us, but also for the other communities and to the larger public.
Hello? Yes. I see a lot of interesting things in your presentation, but mostly focus on the preserve the privacy in the runtime service. But did any focus in the intergroup that about the training data collection part? How we get?
Yes, so that's the differential privacy. So most of that work, especially the multi-party collection of private data, that's one thing in that direction. So it is discussed, but the research paper is like 9 years old. So I think in the wider machine learning community, there's more things to find, but we need to have papers on that also for speech data.
Okay, you mean we need more? This is the only reference we can look right now.
Yeah, there are more references in the survey. I cut it down to some basic examples, but more research is welcome. No?
Oh, okay, thanks.
Okay, thank you very much for your interesting presentation. I think this is very timely. I think a lot of people are suffering at the moment because we have to do with the GDPR and we do speech recording. So regarding these two questions. So I see all over Europe, many people, if they have to carry out an experiment, ethical permission, they have to ask. So I'm wondering, I like it that you have this initiative of this talk and the special interest group. But I talked to our national funding body and I told them, you should try to organize some guidelines. It's not that every researcher has to reinvent the wheels again. Or maybe at the European level, I just talked to you with Clarin, that's the resources organization. How do you think we should tackle this? Because now a lot of people are losing time and money in having to deal with GDPR issues if they have to carry out experiments.
We need to reach out to our colleagues in cryptography in the legal community to work together on this, and we need to do it fast.
Yeah.
Because the horse has already left the barn.
Yeah, that's for sure. And that's the strange thing is that for some time now people would prefer open access. There was a tendency that they say, okay, if you publish in journals, you should also make the data available. We can't do it anymore. Probably, if we look at it in a strict way, we can only use the data, speech data, for one experiment and not again for the next experiment.
And again, for that, it would be lovely if we, as a special interest group, can provide open source code for implementing security measures, privacy measures, and also to have documents that we can share, to establish taxonomies on how the legal community reflects upon, but also what we do, so they can understand us better.
It's time for one quick question. If not, we'll thank the speaker again for a very interesting and timely talk. Thank you.